very much for giving me this opportunity to report. First of all, I'd like to say happy birthday to Professor Yao. The topic is kind of old, older than me for sure. So let me start with this so-called Ambrose-Singer connection. So the talk is based on a couple of joint papers with Professor Lei Ni from UCSD. So I gave this talk at other places before, not in total duplication, but so the contents is that we're interested in understanding a very special type of locally homogeneous Hermitian manifold. So where the Chern connection is Ambrose-Singer in the sense that it has parallel torsion and curvature. So let me start with a Hermitian manifold, which is just a Riemannian manifold on it's a complex manifold equipped with a Riemannian matrix that is compatible with the almost complex structure. And you always have Hermitian matrix. But in order to do calculus, we need to have connections, right? So there are several canonical matrix connections on M. So the most well-known one is the Levi-Civita connection, which is the unique matrix connection that is torsion-free. Torsion is this 2-1 type tensor measuring the symmetry of the connection. So if D is this Levi-Civita connection, it may or may not compatible with J. If it does, that's the Kähler matrix, and everything is good. But if it doesn't, then Levi-Civita connection is not the right connection to use to study complex analytic properties, because it's not obvious what your Riemannian geometric result will mean in terms of the complex analytic property. So here we could say that for as far as compact complex manifolds are concerned, majority of them are non-Kähler. So that's why we. So besides Levi-Civita, there's this Chern connection. So which is the unique connection that is compatible with J and also having 2-0 type torsion. So the 1-1 type of a torsion vanishes. So this is the connection that algebraic geometers like to use, because it exists also on all holomorphic vector bundles, not just the tangent bundle. So there's another connection that a physicist like. So it's the Bismuth or Strominger connection. So this is defined by requiring the connection to be compatible with J and also requiring its torsion to be totally skew symmetric. So it becomes a 3-form. So this connection serves as a bridge between Levi-Civita and Chern. I don't know much physics, so I don't know why physicists you like it so much. But from the mathematical point of view, it kind of serves as a bridge between the two. In the sense that its Riemannian geometry is not as good as D because it does have torsion, but better than Chern connection because torsion is smaller in some sense. For example, the geodesics coincide with the Riemannian geodesics. On the other hand, its complex property is not as good as Chern because it doesn't fully compatible with the whole complex structure. But it's much better than Levi-Civita because at least it's compatible with J. Okay. So when the matrix is Kähler, all three connections coincide. So we're just talking about one geometry. But when the matrix is non-Kähler, then they're mutually distinct. So you have at least three kinds of geometry. So let's recall so from the differential geometric point of view, the simplest space is the space form, namely space with constant curvature, right? And beyond space form, then there's symmetric space that's studied by Chern, right? And then beyond symmetric space is homogeneous space, right? So that's where Ambrose-Singer came in. So we call a metric connection Ambrose-Singer if it has parallel torsion and curvature. So the classic theorem of Ambrose-Singer in the 1950s says that if you have a complete Riemannian manifold, then it's locally homogeneous if and only if it admits a metric connection that is Ambrose-Singer. So the problem with this, so this is kind of like an obvious generalization of Chern's characterization of symmetric space. So locally symmetric space in Chern's theorem is equivalent to having when the Levi-Civita connection is Ambrose-Singer, right? Having the problem is that Ambrose-Singer connections are sometimes not unique. So here, let me, for time concern, let me skip the argument, their main argument. So let me just say that, so there's a lot of questions people can ask. So somehow the study of homogeneous space was popular back then in the 1950s and 60s. But then when Professor Yao and Gromov came along, there are a lot of more modern stuff coming. So this kind of stuff become, in some sense, forgotten. But there are lots of questions, legitimate questions one can ask. For example, if I use this script AS to denote the set of all Ambrose-Singer connections, then you can ask, I mean, this is sort of a moduli space, right? So what is when will this set be a unique point or not a unique point? Essentially, the problem is that when you have a homogeneous space, which means the isometry group will act transitively on the manifold. But there might be a subgroup of the isometry group that already acts transitively, right? So each such group will correspond to an Ambrose-Singer connection, essentially, by their theorem. So you can ask, for example, what's the property of the Ambrose-Singer connection corresponding to the largest, which is the isometry group itself, right? Things like that. So here we just, in the Hermitian version, there is also this theorem by Japanese mathematician, which basically says that Ambrose-Singer connection holds in Hermitian setting in exactly the same way. So here we ask the following question. If I have a Hermitian manifold, then I ask myself, when will one of those canonical Hermitian connections, for example, the Chern connection or Bismuth connection, be Ambrose-Singer, right? So this is a strong way of saying when will the manifold be locally Hermitian homogeneous. This is stronger than locally Hermitian homogeneous, right? So locally Hermitian homogeneous just says you have an Ambrose-Singer Hermitian connection. But here I want a specific Hermitian connection to be Ambrose-Singer. So that's a different situation. So in this work, we basically answer the Chern case. So we call it CAS, Chern Ambrose-Singer. And beyond Chern and Bismuth, you could also ask the same question for the so-called Goldschung connection, which is just the line connecting Chern and Bismuth. So some quick examples. So the Hermitian symmetric space are certainly CAS, right? As when the Levi-Civita as a Kähler case. So in the non-Kähler case, you could so here let me skip. I mean these are the Hermitian symmetric space is a classic topic. So the next example would be the Chern flat ones. So Chern flat in dimension 3 or or higher, it doesn't have to be Kähler anymore. So in this case, this Boothby's theorem says that if you have a compact Chern flat manifold, then the torsion is always parallel. Therefore, it's Ambrose-Singer. They're essentially the quotients of complex Lie groups. So, for example, this Iwasawa manifold is the simplest kind of example. So, so our question, the first question is, are there any other examples? You can take products, right? Things like that. So there's another question related. This is the classic theorem of, we call it AK theorem, right? So, so it says that if you have a homogeneous manifold, then if it's Ricci flat, then it must be flat. Okay. So by the way, there's an interesting anecdote. So this is before Professor Yao's solution to Calabi conjecture. Right before, right? Back then, people don't know any example that is Ricci flat but not flat. Back then, there's no such example, no. So therefore, back then they are asking more conjectures. But at least in the homogeneous case, it says that the thing we call Calabi-Yau cannot exist, right? Okay, so our main result says that essentially it's a negative result, it's a non-existence result. So if you want the Chern connection to be Ambrose-Singer, then you only get the trivial examples, the Hermitian symmetric ones or the Chern flat ones. So that's the, so, or their product. So, because of time, to save time, I'll just say roughly how the proof goes. Basically, the proof contains three parts. The first part is we want to extract the Kähler-Durand factors. You want to split off these Kähler factors. This is standard. Here, the argument, you cannot use Durand decomposition because the connection will work with torsions. So so the standard Durand decomposition theorem fails. So you have to do a little bit of analysis. The second part is to show that now you don't have the Kähler factors, right? The non-Kähler factors you want to show is Ricci flat. So that's the second part. This is through local analysis. And then the third part, basically, we need a AK type theorem to show that Ricci flat leads to flat. Okay. So, but here we cannot apply AK theorem, which only works for Levi-Civita connection. Here we're working with connection with torsion. So basically, what we need is an algebraic version of Simon's holonomy theorem. So, but we need to generalize it. So Simon has this famous paper giving an algebraic proof of Berger's holonomy theorem. So, but what we need is basically something like Simon theorem, but instead of Levi-Civita connection, we need to work with a connection with torsion. So, so let me skip this this proof part. Let me get to the end of it. So in particular, as a corollary to our negative non-existence results, we get AK theorem, AK type theorem, at least for Chern connections. So so that's the main corollary. So if you have a Chern-Ambrose-Singer situation, then Ricci flat means flat. So I should point out one thing. So there is a naive way of generalizing AK to Chern connection. Namely, if you require just locally homogeneous, then Chern-Ricci flat doesn't lead to flat. Okay, there are counterexamples. The reason is in the non-Kähler case, you have three different Riccis, right? So if you just want one of them to vanish, the other two may not vanish. But I don't know of any example, counterexample to if you require all three Ricci, Chern-Ricci to vanish, and yet it's not, and plus local homogeneous, but then it's not, then it might be Chern flat, I don't know. So that's still an open question. So we list that as an open question. If all three first, second, third, all three Ricci vanishes. So now for Gaussian connection and for Bismuth connection, this question is much more interesting. And so far we only have very limited results. So we call Bismuth BAS. So basically require Bismuth connection to be Ambrose-Singer. Unlike the Chern case, there are examples of not locally Hermitian symmetric and not Bismuth flat yet Bismuth Ambrose-Singer. There are lots of such examples starting in dimension 3. Bismuth flat are the Samuelson spaces. So here, let me skip that part. And in particular, you could ask the AK type question for Bismuth connections. So our partial results basically says that the question, the AK type question for BAS manifold. First of all, the classification of BAS manifold is an interesting question. This is a smaller set than the so-called natural reductive homogeneous spaces. I think it's much more realistic than is Gibber's attempt trying to classify a natural reductive space. So far, they're only successful up to real dimension 8. So the AK theorem, what we can show is in complex dimension less than or equal to 4, then if it's Bismuth Ricci flat, then it will be Bismuth flat, assuming Bismuth Ambrose-Singer. So there are related questions like this Garcia Fernandez streets. So their conjecture was recently disproved by Podesta. So another conjecture is raised by Professor Yao and Zhao and myself several years ago. So we consider, this is similar, we consider the so-called Bismuth Kähler-like manifolds, which means Hermitian manifold whose Bismuth curvature obeys all the Kähler symmetry, yet it's non-Kähler. So CYT means they have vanishing first Bismuth Ricci curvature. But in the Bismuth Kähler-like case, all three Ricci are the same. So this conjecture was recently proved by Zhao and myself. So CYT it means Calabi-Yau with torsion. So this is a term they use, meaning that the Bismuth connection has SUN holonomy. So this is recently proved by Zhao and myself. Okay, so here let me skip the discussion on the Gaussian case. Oh, let me mention one example. So these BAS manifolds, if you consider three-dimensional ones, they can be balanced, unlike the BKL ones. BKL ones are always non-balanced unless they're Kähler. So the balanced ones are particularly interesting. So according to this so-called B rank, the rank of the B tensor, which essentially comes from the square of a torsion. So if the B rank is 3, then it's a complex simple Lie group, okay, compact quotient. And if the B rank is 1, then there is this flag manifold, so we call Wallich threefold. It has to be a Fano threefold of index 2. So it turns out that so-called Del Peso threefolds, only one of them qualifies. That's the Wallich one. So it's the projectivization of the tangent bundle of P2. And then most of these balanced BAS threefolds are so-called middle type, namely the B rank is 2. In this case, there's they're corresponding to the so-called Bismuth abelian type of Westman threefolds. So we have a classification theorem, which is kind of interesting. So so here I wrote down a specific soft manifold example. So that's the middle type. So this soft manifold has vanishing Chern-Ricci, but it's not Calabi-Yau type. in the sense that its canonical line bundle is not trivial. So this is why those people in the algebra people, they didn't discover before. So, okay, thank you very much. Okay, stop here.
So Sergey, I save a few minutes. Any question, comment?
Suppose I take a Hermitian metric, I want it to be balanced, and then I want to look at all connections, which is make sure it preserve J and also preserve omega.
Omega is a holomorphic N form. Okay.
Yeah.
Okay.
Well, I mean, the holomorphic N form.
Okay.
And one cast by those.
That's a very interesting question. I thought about it a little bit, but I don't have any results yet.
See, what physics wants is SUN connection, and we want a supersymmetry to be there.
Right. I thought about the homogeneous version.
Balance condition is make sure the Cater form is supersymmetric.
Right.
So I mean that's what needs.
Okay, I'll think about it. Yeah.
Any more questions or comment? So I have a naive question. So when you talk, for example, BAS, they call the first B-rich, second B-rich, and so on. Yeah. So if I want to consider non-Kähler Calapi-Yau, you have three rich conditions. You need to prove three kind of theorems also.
Yes. So when you talk about Einstein matrix, for instance, in the non-Kähler case, you have different kinds of Einstein. First Chern Einstein, first Bismuth Einstein, second Chern Einstein. Yeah. So you have at least according to Kefeng's paper, there are at least 6 types.
So there would be many more.
They're related,
different kind of Calapi-Yau theorems to be proved.
That's right.
Okay.
Yeah.
Any more questions? If not, we thank Professor Zheng again for a very nice talk. So we end the first session and the second session after tea time. I think it's around 3:20.